Hello, and this is Professor Michael Chi from the Center for Sleep and Cognition at the Yong Lu Lin School of Medicine at the National University of Singapore. And I'm pleased today to make a presentation entitled Measuring Sleep at Scale Using Consumer Sleep Technology. I'll begin the first few slides showing myself, and then I'll happily disappear because these slides are at high resolution and they contain a lot of valuable information for you. Just by way of background, I am formerly trained as a neurologist, and I've been doing fMRI research initially, and then I switched to researching sleep with fMRI, and then most recently with wearables and large-scale data. And this is what the talk is based on. So today you're going to hear about the original and still good reference for sleep measurement, polysomnography, the types of consumer sleep technology or CSTs, the growth of consumer sleep technologies and why it matters to researchers and clinicians, the features of sleep physiology measured with wearable CSTs, and then the all-important question about how accurate they are and for what they're useful for. Related to this is how we can integrate sleep-related information from different channels to give us an accurate longitudinal read about how people sleep. And finally, I'm going to present some examples from our work about how consumer sleep technology can be used for research. And I hope this presentation inspires you to look more into this very interesting and growing field, and that you will make an impact to your research as well as to the people you care for with this knowledge. Consumer sleep trackers have been in existence since around 2009, but it's only in the last 3 to 5 years that they have shifted from being viewed as mere gadgets to serious contenders in the public health and sleep medicine space. Multi-channel EEG, the reference technology for sleep measurement, has been in existence for close to a century. Now, recent advances in automated sleep staging aside, the basic approach to data collection and interpretation has remained stable for many years. Now, the deployment of PSG for sleep assessment is largely confined to the clinic or the laboratory because of how resource intensive it is. Actigraphy, which preceded consumer sleep technology, has been around for about 50 years. Now, it overcame the scalability and field deployment constraints of PSG with some trade-offs, but again, it was mainly confined to expert users. Now, Fitbit burst on the scene in about 2009, riding the wave of interest in health gadgetry and fitness tracking. The addition of multiple sensors, convenient data collection, storage on the cloud, bundled with aspiration-fulfilling data displays, has taken place over a very compressed timeline. This has opened the door to many new users. In today's talk, I will classify CSTs under 3 main groupings. The largest and most significant of these is non-EEG wearables. And these can be divided into well-validated and mass-market devices for reasons that will be apparent later. EEG-based systems were prosumer devices for a period, but are now mostly out of reach of consumers. Importantly, while they are quite comfortable in my opinion, they are not tolerated for daily use by up to a quarter of persons. Non-EEG wearable sleep trackers are the largest group of devices. Now, while they look the same superficially, except maybe the ring form factor and armband devices, they differ significantly in price and/or performance and/or functionality. Finally, there are the nearables, which aren't worn but are instead placed somewhere off-person in the sleeping environment. These harness movement-generated electrical signals or pulse radio waves to derive the requisite physiological signals to infer sleep. Now, because the annual revenue growth for digital fitness devices has been in the 6% range, or rather large, It has attracted many clever people to develop new tools and applications. However, money drives business, and sleep, while important, is not the top reason why the average consumer buys a health tracker. So, those of us in the research and clinical communities have a vested interest in shifting this, and I hope to convince you why. Right now, our hours of careful thought and application of scientific method, often matter less to the average consumer than the well-crafted social media trained output of lay writers. This is somewhat reflected in a survey conducted by Steve Hirsch's team about what features consumers think are important in a sleep tracker. Notice, for example, how sleep staging appears as the number 2 feature, while limb movement, the major contribution to information about how to perform sleep-wake detection, is put at number 10. The corresponding response from experts is quite different. Sleep depth, for example, is underweighted by experts. Both groups, however, tend to underweight items that are important for sleep health, for example, sleep regularity. I would argue that a greater convergence of interest is vital for sleep to have greater influence in health and well-being spheres. A comparison between the rise of camera tech and sleep tech is merited. Specifically with photography, what was previously only in the hands of well-heeled enthusiasts is now widely available. The reason for this off-the-chart transformation in sales after 2010 is clear to see in the next slide. Which image was shot from a professional camera? This is a great illustration of the image quality achieved by modern smartphones aided by computational photography algorithms. Now, wouldn't it be great if some of the brain trust enrolled in digital photography could be employed in sleep science or medicine? So, takeaway 1 is that consumer sleep tech is here to stay. So, let us learn how to ride that wave. Now that I've stimulated your interest, let's get down to business. Wearables evaluate a set of physiological features generated from subcortical and brainstem outputs as distinct from thalamocortical influences underlying EEG signals. However, it is the same brain state we are surveying, although through a different lens. Now, EEG-based sleep assessment has decades of history. On the other hand, we're only beginning to harness the power of autonomic signals combined with behavioral markers to better understand sleep. This point is underscored by the finding that neuron clusters involved in arousal and action have intertwined influences on EEG and autonomic activation. Motion, heart rate variability, temperature, and for neurables, respiration, enter into models that classify wake or sleep and then run staging. Tabled here are several physiological changes that occur at different stages of sleep, which you can review at leisure. Now, while the basis for CST measurement of sleep is known, the type of sensor, their placement, how consistent their measures are in the field, and the algorithms used differentiate devices. Then, there is also a user factor. In the inset, my sister here illustrates how not to wear a smartwatch if you want good tracking data, and that's because it's too loose and it will result in loss of good PPG signal. I'll go into a bit of detail about the technology underlying the measurement of the different physiological markers that underlie CSTs. The most important of these is motion detection or actigraphy, which is typically measured in different directions using a solid state device called a MEM sensor. This is a microelectronic mechanical system that has circuitry that generates a current when movement within the sensor occurs. To translate these movements or electrical signals from movements into sleep inference, 3 types of actigraphy algorithms have been implemented. They are so-called zero crossing, time of birth threshold, and proportion integration method. You can read about these details in this journal, but it suffices to say that they differ in the manner in which significant motion is detected and graded, and their names are informative about what these differences are. To infer the transition from wake to sleep, motion for some minutes before and after the current minute of activity are taken into consideration. This ensures that there is some continuity to a perceived change in state before it is flagged as such. Now, sensitivity to motion can be adjusted for study purposes. For example, the sampling window can be changed, as can sensitivity to motion. For children, sensitivity often needs to be reduced, or sleep will tend to be underestimated. The reverse may be true of an older adult who moves a lot less during sleep and may be also relatively more still when awake. Actigraphy has several strengths. It is the best studied of non-EEG sleep measurement technologies, and the effects of age and disordered sleep have been evaluated. You can hand out a device and leave it unattended for a week, 2 weeks, sometimes even longer. And then finally, it uses a few well-documented algorithms. Also, for researchers, the sleep measurement can be tuned post hoc to adjust for particular characteristics of that group. Of course, all of this takes prior knowledge about how to do this, and then expertise is not common in groups that don't have deep experience. There are also several disadvantages to actigraphy. Firstly, one is unable to monitor the participants' daily compliance, because most of these devices don't store their data on the cloud, and it's difficult to monitor how your participants are doing. They were relatively more costly. They are more closer in price to consumer devices, but they're still quite costly per unit. They don't have any added functionality beyond sleep measurement. Then the measurements from different manufacturers also differ slightly. So they are touted as being research actigraphs, but in truth, the outputs from different devices do have subtle differences. And finally, as I alluded to earlier, it requires significant expertise to handle or tune the raw sensor data to truly get the best value from a research point out of these devices. There are also several lesser facts about these research-grade actigraphs that need to be pointed out. The first is that the training data sets used to verify the algorithms were relatively small relative to what's possible today. A lot of consumer sleep trackers are criticized as being not validated, but in truth, some of the new validation studies involve far more subjects than those used to train these research actigraphs. Secondly, and I'll mention this the third time, is the ability to collect raw data is potentially useful if harnessed, and this requires expertise to mine, as I stated. Most users, in contrast, will use default sensitivity settings, and a presumption that because these devices were used in research, they are somehow more trustworthy than consumer sleep tech is just generally not correct. Now, one criticism of consumer sleep tech is that firmware changes take place, but these also occur with research-grade actigraphy, although the announcements may be clearer, and it can affect measurement. And finally, outputs from different devices can yield different results, as demonstrated in this paper by Liu, which you can look up. Now on to PPG, or photoplethysmography. This is a simple optical technique used to detect volumetric changes in blood in peripheral circulation. It is a low-cost and non-invasive method that makes measurements at the surface of the skin. The technique provides valuable information related to our cardiovascular system. Now, medical-grade PPG makes use of low-intensity infrared or IR light. So when this light travels through biological tissue, it can be absorbed by bones, skin pigments, and by both venous and arterial blood. Now, since light is more strongly absorbed by blood than the surrounding tissues, the changes in blood flow can be detected by the sensors as changes in intensity of light. The voltage signal from PPG is proportional to the quantity of blood flowing through the blood vessels, and this is the basis for this technology. Now, the sensors differ in terms of whether they are transmissive or reflective, and the wavelength of light used by the sensor. Now, the most commonly used wavelengths are green and infrared. Now, green is common in wearables, particularly those at the wrist. They're good for measuring pulse rate, but because its tissue penetration is rather low, it's good for that pulse rate estimation, but it doesn't enable oxygen saturation, which requires a different wavelength, or the PPG waveform analysis that I'll talk about later. Now, the main use of these PPG signals in wearables is to obtain heart rate, and from that, heart rate variability when you string a succession of pulse detections together. So heart rate variability refers to the beat-to-beat variation in heart rate, and it can be measured in the frequency or the time domain. The time domain form of analysis is more readily understood, and it uses successive time intervals between a series of heartbeats. The most common measure used is RMSSD, or the root mean square of the successive intervals between the detected pulses. Frequency domain analysis uses Fourier transform data where a time series of pulses is transformed into plots of the magnitude of expression of particular frequencies. The two most important measures are LF and HF, with HF, in my opinion, being more important because it more completely reflects parasympathetic signal influences that are strong as we descend into deeper non-REM sleep. So an optimal level of HRV is associated with good health and self-regulatory capacity, adaptability, or resilience. Higher levels of vagally mediated heart rate variability are also linked to performance of executive functions like attention and emotion processing. HRV tends to get lower as we age. On the left, we see a panel showing the increase in the RR interval. That means the heart rate is slowing as we descend into deeper non-REM sleep and then becoming more erratic in REM. And this is consistent with the greater parasympathetic influence as one descends into deeper non-REM sleep, but the mixed influences of sympathetic and parasympathetic systems in REM. Now, this slowing of heart rate is also accompanied by greater heart rate variability. Now, you can see this in the time domain, but also when you do the Fourier transforms, you can see this in the frequency domain. Now, HF power, I mentioned earlier, is a good indicator of parasympathetic activity, and notice how it increases as one descends into deeper non-REM sleep. Temperature sensing is a measure used by some devices, and it's based on the fact that core body temperature starts falling about 30 minutes before one falls asleep. And this fall in core body temperature is accompanied or is achieved by increasing peripheral blood flow, resulting in heat dissipation on the skin. So you can see the reciprocal relationship between core body temperature and the distal skin temperature. Now, there is a sleep as well as circadian influence on this core body temperature, with the nadir being reached 2 to 4 hours before awakening. This occurs in dawn. Now, older adults have difficulty in resuming sleep during the ascending core temperature in the morning. Now, stress also disturbs peripheral heat dissipation and impairs sleep, whereas hypnotics tend to induce peripheral vasodilatation and encourage sleep. Here we can see concurrent accelerometer and temperature data for one participant. It's a bit unfortunate that the color coding used by the authors is such that the colors for deep sleep and wake somewhat overlap, but clearly this is at the wake stage, where you can see there's quite a high degree of motion, and then this decreases as one descends into sleep. And then you can see that there is, at the sleep onset, a rise in the peripheral temperature corresponding to the drop in core body temperature, and the fact that there is a drop in the peripheral temperature corresponding to a rise in core body temperature during REM sleep, and so on. Now, the inverse is of temperature changes in the periphery. Distal periphery is mirrored here in this diagram from Carucci and DeBoer, showing that at sleep onset, there is quite high core body temperature, and then it drops during deep sleep or slow wave sleep, where there's high slow wave activity, and then the core body temperature rises during REM sleep, where the EMG is very low. So that's it for temperature sensing and sleep. Now, some manufacturers put in a weighting about sleep staging based on prior knowledge about the macroarchitecture of sleep. And from previous lectures, you know that there is a macrostructure in sleep. N3 is more likely in the first half of the night, REM more likely in the second half of the night. This is integrated into some algorithms to increase the weighting of detection of particular sleep stages at different parts of the night. Finally, I'll touch on the changes in respiratory rate by sleep stage. Now, on the right panel, notice that during wakefulness, respiratory rate variability is highest, and during REM, it's intermediate between non-REM and wake. So as we descend into deeper non-REM sleep, you can see that respiratory rate variability gets a lot lower. And then you can see in these nasal pressure signal plots that there is quite good regularity in stage N2, which is a non-REM stage. During the Fourier transform of this RRV signal you can see a higher, more distinct peak in the first harmonic, indicating higher regularity, whereas during REM sleep, which we have pointed out, a stage where it's intermediate between wake and deeper non-REM sleep, the respiratory pattern is more irregular, and that's reflected also by a reduction in amplitude of the first harmonic, and then a greater sort of spread of amplitude of frequencies in neighboring frequencies. Now, there are different signals used, and I mentioned that analysis of motion is by far the most important contributor to sleep-wake detection. The next most important physiological variable is heart rate variability, and here a sampling of multiple works about this. In this slide, you can see the differential benefit to sleep staging contributed by the different physiological factors. And I've mentioned several times now, motion detection alone does a pretty good job with wake-sleep classification. But there is a big jump in the ability to detect N3 and REM when heart rate variability enters the staging model, and it explains why it is so widely used in current consumer sleep technologies, and the emergence of ECG-only systems as well. So takeaway 2, concluding this section, is that the sensor technology and the physiological basis of sleep estimation using consumer sleep technology is well-founded and has been tested in laboratories, but the quality of implementation matters. I'll next deal with an overview of the strengths and weaknesses of wearable sleep trackers. Perhaps it's appropriate to point out that until quite recently, and maybe persisting in some places, there is a bit of a bias against wearables because of reasons that are founded as well as not founded. And these are summarized in this paragraph written by Chris Deppner in an editorial piece written in Sleep. There are some genuine challenges with wearables at the present time. Firstly, there are no currently enforceable standards for minimal quality. Secondly, the algorithms are black box. There's a good reason for this, but this results in differences of methods that need to be reconciled in some form or another. Then there are continual firmware and hardware refinements which make it challenging for longitudinal studies. However, for each of these three concerns, there are workarounds. For example, you're going to hear about some recommendations for how you assess the quality of the output of sleep trackers. The output from black box algorithms might be normalized through third-party providers, and the continual firmware and hardware refinements in longitudinal studies can be controlled by version locking in the more enlightened manufacturers. Then, of course, there's the measurement issue, which you will hear about shortly. Persons who lie very still in bed prior to falling asleep can give rise to inaccurate readings. Few devices measure naps reliably. And finally, the intense competition in the consumer space makes one bad choice by a manufacturer quite challenging, and it can sometimes even lead to bankruptcy, which can hinder longitudinal studies. This said, there are very strong reasons why wearables are compelling. They are much more affordable than the research devices. They enable the collection of longitudinal data, and I'll give you some examples of case studies of this. There are many existing other uses of the wearables besides measuring sleep. And finally, there are future features to look forward to within device and cross-device information integration, which I will illustrate in subsequent slides. The big question, though, is, are they accurate enough? And enough for who? There are a good number of validation studies in the last 5 years, and this indicates growing interest in deployment of CSTs by professionals. There currently exist several common recommended frameworks for evaluating wearable sleep trackers. The challenge for scientists and clinicians is not how to do the good evaluations, but how to get resources to test properly when money can be made by manufacturers from not bothering to do so. We think this will change with time. Now, walking through some of these tests, I will make points about the positive qualities as well as the limitations of CSTs. Blair-Norman plots shown here inform us how biased measurements from that device are in comparison to reference PSG. We can also gauge how this bias changes along lower and then higher values of that measure, the so-called proportional bias. Device bias within 30 minutes of a reference measurement is generally accepted as a good standard to aspire to for total sleep time measurement as shown here. These limits are denoted by the green band. Note that in participants with high sleep efficiency, marked by the black dots, bias or discrepancy tends to fall within a good specification. Conversely, persons represented by the blue dots, in whom sleep efficiency was less than 85%, tended to have off-the-mark measurements. Inaccuracies in sleep measurement arise mostly from deficiencies in wake detection when a person is awake but motionless. In these comparative two-stage hypnograms, the PSG reference is at the top row. Automated bedtime detection is a consumer feature needed for the calculation of sleep efficiency. It's not present in PSGs, but this makes the estimation of sleep parameters more feasible for consumers who don't often indicate when they intend to fall asleep. Estimating bedtime and thereafter sleep latency are easy if there's a dramatic change in movement soon after intending to sleep, as shown here. This might be adequate on many nights in healthy persons. However, this assumption will falter in field conditions on some nights, even in healthy sleepers, and on many nights in persons with difficulty falling asleep. A quick fix can be had by having the user open the app before going to sleep. Fitbit does implement this feature. However, the company found that few persons actually use the feature even when it's provided. A bigger problem occurs when one wakes up and then lies still, as shown here. Now, with this device, the wake period is accurately detected, but at other times, such periods are misclassified as sleep. Now, you can see that the quality of detection of such wake periods after sleep onset differs across the three types of devices shown here. In this comparison of four-stage sleep classification using different devices worn by a healthy young adult with high sleep efficiency, you can see that the EEG headband and the reference PSG system have hypnograms that are almost in perfect synchrony. Note also how well the two higher-end consumer sleep trackers detect and stage sleep. On the other hand, the low-cost device, an example of which is shown here, did not do so well. In this example, the young participant's sleep was highly disrupted. One reason being discomfort wearing the headband, so there's lots of periods of wake after sleep onset. Even with this, the EEG headband performed excellently. However, in this instance, when sleep efficiency is reduced, even the better CSTs tended to falter in their performance. Notice how when the person was awake but motionless, the better CSTs sometimes got it right, as illustrated here, but were fooled more times than not. When reading reports about accuracy, particularly when only healthy participants are tested, beware of overreading the labels accuracy and sensitivity, because even a mediocre device will score in the 90s, the high 90%, because in healthy test subjects, most of the testing time is spent asleep. Detecting quiet wake precisely is what sets apart the better devices, and the more discerning metrics are specificity and kappa. These are pretty decent with the leading CSTs compared to a research actigraph set at its default settings. In four-stage multi-class classification, focus on which device has larger numbers along the diagonals of these so-called confusion matrices. You can see the difference between the iteratively improved higher-end CST and the low-cost device in this matrix. Now, an important point is that aging erodes classification performance. However, CSTs are in good company because even with EEG, the certitude or certainty with which sleep can be staged declines slightly with age. And this is also true of research actigraphy. I mentioned earlier, but it bears repeating, that another weakness of CSTs is that short naps of 15 to 30 minutes are not reliably detected. It's still an evolving feature. With these caveats in place, it's good to know that a consumer sleep wearable was shown to match the performance of research actigraphy when studying patients with insomnia in the laboratory. Also, in a field setting where the device was as capable in detecting intervention-induced sleep changes as a research actigraph. Mind you, these reports appeared in 2017 before an upgrade in Fitbit's sleep algorithm. Rounding up, what constitutes a good enough device depends on the use case. Now, you don't need an atomic clock to tell time, but you need one for accurate GPS navigation. Across a sample that included persons of different ages, our performance evaluation that's now published in Sleep Health threw up 3 recommendations. For the first group of users requiring very accurate sleep staging performance in patient studies, such as clinicians or researchers studying samples with sleep disorders or persons with fragmented sleep, an EEG-based wearable with 2-stage and 4-stage kappas of between 0.75 to 0.8 is what's recommended. However, for most studies, especially those public health studies evaluating sleep longitudinally in persons without highly disordered sleep, a high-end consumer sleep tracker is more than adequate, and these, mind you, keep improving. These have a 2-stage kappa of about 0.6 to range up to 0.7. I cannot conscionably recommend devices in this third category for any serious user, but if you need a low-cost sleep minder, these work. The hope is just as basic features in today's smartphones were advanced ones just a few years back. We hope that this group of CSTs will be driven to improve over time. However, in the present day, the issue is not so much accuracy. It's focusing on users that make a material difference to health and well-being. There is a huge opportunity to obtain large-scale data on duration, timing, continuity, and regularity with existing trackers, high-quality trackers, and this is what we should focus on. I mentioned earlier that the assessment of sleep debt is underweighted by experts compared to consumers. We now know that slow-wave sleep is important physiologically, but it does not relate to feeling deeply asleep. Also, the duration of N3 is not convincingly related to memory consolidation. So it is not helpful for laypersons to compare how much deep sleep they have because it is influenced by physiology and disease, but it's not something that can be readily increased, and people shouldn't fret if they don't meet the expectations of their peers. There are far more important concerns, like, are we collecting sufficient data on persons who stand to benefit the most from sleep improvement? Here that we can see that in the ABCD study on adolescents conducted in the US, those less likely to keep wearing their devices even for a 3-week period belong to segments of the population who are known to have poorer sleep, those in particular ethnic groups and those who are socioeconomically less advantaged. Now, if CSTs are to gather information that can improve public health, ways and means to engage such persons are needed. Greater geographic coverage is also needed. With wearable or large-scale survey data, only a few countries are truly well represented across the globe, and this point was recently highlighted in a Lancet Public Health article which looked at the data available about sleep duration in different countries. We await the day when CSTs gain broader adherence like smartphones to enable us to gather global coverage information about how people sleep across different cultures. So takeaway number 3 is validated CSTs are accurate enough for assessment of a relatively healthy person's sleep. The challenge is to gain more representative and comprehensive understanding of sleep with them. I next move to expanded uses for existing sensors. Now, the PPGs embedded in CSTs already have multiple uses that are shown here, but there will be new ones, and I will dive into 2, arterial stiffness and blood pressure. The PPG signal is not just a pulse, but there is a waveform associated, and this can inform about the state of the arterial stiffness. Arterial stiffness is important because elastic arteries help cushion the impact of the ventricular ejection of blood, which helps lessen forces that could otherwise damage organs like the kidney or the brain. Elasticity also results in improved diastolic perfusion of organs like the heart. Now, as we age, our arteries stiffen, resulting in increased pulse wave velocity. The PPG waveform changes with age can be seen by the loss of the dichrotic notch in older persons. Now, acquiring high-quality PPG waveforms may be challenging when one is awake and moving. The signal is much cleaner during sleep. Further, as a colleague of mine, Jism Yilmaz, demonstrated, the waveform changes with descent into non-REM sleep reflect arterial relaxation. Look at how the dichrotic notch becomes clearer in the PPG of a young participant as that person descends into N3 compared to when they were in light sleep. This is consistent with the greater parasympathetic influence on vessels in this deeper stage of non-REM sleep. Notice that the changes are significantly attenuated in an older participant. Expanding on these points a little, waveform analysis identifies fiducial points from which various vascular stiffness metrics can be evaluated. These metrics show sleep stage specific changes. Now, arterial stiffness indices also show age-related changes that differ across persons. So future work can explore how changing modifiable lifestyle factors, including sleep, can modulate vascular stiffness with age. Now, the fingertip PPG can also be used to obtain cuffless blood pressure measurements based on the analysis of waveform characteristics. Our collaborator, Thomas Yeo, applied machine learning to achieve respectable prediction of performance for both systolic and diastolic blood pressure using fingertip PPG data. A mean absolute error of about 5 millimeters mercury, which is considered very adequate by industry, was reached. There was also good within subject agreement between the predicted and the true blood pressure readings. And this high correlation is impressive in the order of 0.6 for 96 for both systolic and diastolic blood pressure. Now, the stiffness index referred to earlier turned out to be a key feature contributing to this kind of blood pressure prediction. These findings are significant because PPG signals during sleep show a greater range of variation and are less susceptible to motion artifacts. This makes sleep an ideal state for the detection of nocturnal hypertension that could otherwise be masked during the day. The dream is to be able to track how blood pressure reacts to different environmental exposures, including sleep loss, and how intervention might modulate this. So the takeaway 4 is that one should watch out for novel uses of existing sensors. Now, knowing more about others helps each of us place ourselves within the bigger picture. Passively following sleep over months fills an important gap in our knowledge about what good sleep means. Sleep variability is emerging as a dimension important to sleep health, and a long duration of data acquisition is important for its accurate determination. However, many large epidemiological studies to date that have linked greater sleep variability to higher mortality have tended to evaluate sleep variability only over a limited time, typically around 5 days of actual data. Some studies don't even take into account weekday variation when assessing sleep variability. My team systematically examined how sleep duration and timing data of 576 persons who each contributed an average of 220 nights of data influences estimates of sleep variability. And we found that good estimates of total sleep time variability required 5 to 6 nights for weekly time windows and between 11 to 18 nights for good estimates of monthly time windows. So more nights matter. The point is that missingness is often not random, making longer data collection better for reducing the influence of missing nights where one may have deliberately avoided having sleep measured. An example of this is when we were doing a study on students and they omitted providing data closer to the time of the exams because they felt that they did not want to achieve poorer sleep scores during that time. Here is a study that got the assessment of sleep variability right by evaluating it over at least 28 days. Alongside, the authors obtained at least 5 blood pressure readings per participant. This allowed the authors to confidently state that sleep variability is a predictor of risk of hypertension independent of sleep duration. What are the relationships between sleep duration, timing, and regularity across the world? We took a stab at this question by using de-identified data from Aura involving 220,000 adult-age users from 35 countries. Data from an average of 242 nights per wearer replicated previous findings that weekday sleep duration is shorter and that it starts later in Asia compared to other regions in the world. Now, despite this, sleep was both less efficient and more variable in Asians. Now, normally if you curtail sleep, it becomes more efficient. Normally too, variability should scale such that with shorter sleep, it should be lower. However, this was not so here. Now, previous findings from the UK and US suggest this to be unhealthy, and there may be, in the words of a reviewer, a health tsunami coming to Asia with ripple effects elsewhere. Now, a contributor to greater sleep variability on weekdays was the smaller weekend sleep extension that was lower in Asia compared to Europe and Oceania. Note that weekend sleep extension is not the same as social jet lag, whose continental differences were less clear. Now, we posited that the perennially short sleep without significant weekend relief drives Asians to catch up on sleep whenever they can, driving up weekday sleep variability. While others may have observed some of these points before, the importance of cultural differences in work and societal norms has not been highlighted previously. So we don't think it is latitude that accounts for sleep duration differences in many instances. This is because countries like Singapore and Japan are at different latitudes but sleep similarly, whereas countries at the same latitude difference from the equator like Japan and Australia have rather different sleep patterns. So we think that it is culture and especially work And you can see that there are significant continental work hour differences between different regions. And these can have bidirectional effects on time use and other domains like sleep. Now, trackers may also be invaluable in identifying how society-wide events affect sleep. On this plot, orange lines depict bedtime across weeks in 2019, and the blue lines sleep timing in 2020. Notice the pattern of later bedtime on weekend nights and how this punctuates the weeks across both years. Now, this rhythm was transiently disrupted by the major Lunar New Year holiday occurring asynchronously across the 2 years. Now, the announcement of a global pandemic in March 2020 had little effect on bedtimes until businesses started closing and movements were restricted. Now, this underscores a point that sleep habits are just that. They are very entrenched, and it takes something massive to change them. But the pandemic was big enough to do that, and you can see the shifting of bedtime and wake times such that people spend a bit more time in bed during COVID and achieve longer total sleep time. As sleep trackers also collect the timing of physical activity, we can construct temporal profiles of a person's physical activity over 24 hours. This allows us, after clustering the collective rhythms of the entire sample, to yield 4 main rest activity rhythms, or RARs. Now, notice that the most active green RAR has a light brown counterpart, and how the blue 3-peak RAR has a less active red counterpart. These broadly correspond to weekday RARs and their weekend counterparts. Notice also how temporal fluctuations in the relative predominance of RAR expression can be visualized across weeks and months. Notice how the cool-colored weekday RARs dominate on weekdays, but give way to the earth-toned RARs over the weekends. Notice also how after the COVID lockdown period, the preponderance of RAR patterns in the entire sample shifted such that more persons were expressing the weekend type inactive RAR patterns. Isn't this a nice demonstration of how behavioral tracking can inform about the effect of a society-wide influence? So takeaway number 5 is long enough data collection reveals how sleep varies over time, person, culture, and circumstance. Now that we have demonstrated the utility of longitudinal data from a single source, let's move on to how we can expand to harnessing sleep information from multiple sources. Multimodal data collection provides for data redundancy and garners additional sleep-relevant information to enrich the value of the device-collected sleep data. The collection methods depicted here piggyback on the fact that a smartphone is already needed to utilize a sleep tracker. So why not also collect other relevant information alongside? Now, to fully benefit, a change in mindset is required from us. That is, to shift from thinking of assessing errors within individual channels of information to thinking of how several imperfect measuring methods can be combined or integrated in a way that allows algorithms to cover for the weaknesses of each individual channel. When Steinmaster originally collected data from university staff and students, the original intention was to test compliance and data agreement from three sources: a sleep tracker, an app that measures when and how you use your smartphone, and an EMA sleep diary. There was more than 80% compliance over 8 weeks and excellent agreement between the three channels. But on 23% of nights, there were discrepancies where one channel had a greater than 1 hour difference in sleep assessment compared to the other two. When analyzing the pattern of these discrepancies, we found 3 different patterns, but I'll just focus on one to illustrate how shortcomings in wearable sleep assessment can be overcome from by data from other streams. Here, the blue periods are the ones where at least 2 of the 3 channels agreed on classifying sleep. The gray bars indicate the intensity of phone interaction, and the blue lines indicate when Aura detected wake-up time. Aura correctly indicated these wake-up periods on the first night, but misclassified wake as sleep when the participant was using a smartphone with little motion on these 2 nights. Now, the raster plot shown here, where each person occupies 1 row and each column represents 1 night, you can see that membership to a particular discrepancy pattern, here the pink discrepancy pattern, is quite trait-like in that most of the nights where there are discrepancies, the same pattern of discrepancy is expressed. The club that most often showed this first pattern here was unsurprisingly dominated by younger students who wake up with their phones and go to bed with them. Speaking of students, our collaborators recently demonstrated how detecting the use of any of a registered user's multiple Wi-Fi connected devices can inform about likely sleep-wake state. This was done at scale without any additional device purchase or app installation using campus Wi-Fi logs. More on students because their mental well-being is so important. Alyssa Ng studied a sample of healthy but relatively sleep-restricted university students, asking them to rate their mood, motivation, and sleepiness twice a day using a smartphone app. They also wore an Aura sleep tracker for 2 to 6 weeks. This allowed us to collect 2,471 nights of sleep data and multiple post-wake and pre-bedtime assessments. We also assessed about 1,018 naps. Multi-level modeling was conducted to make inferences, and what we found was that on nights where sleep was longer than the participants' average were associated with better mood, higher motivation, and lower sleepiness in the post-wake window. Better scores in mood and sleepiness persisted also into the pre-bedtime period. Now, time-lagged analyses showed that these effects were limited or constrained to the day after a given night's sleep, so lending credibility to the issuance of daily mental readiness scores. Now, what was important is that a person's average sleep duration did not significantly predict between subjects' differences in average mood or motivation ratings. This speaks to the significant inter-individual differences in the amount of sleep necessary to benefit mood and motivation. In contrast, greater intra-individual sleep variability had negative impact on mood and motivation ratings, extending previous work showing negative mental health consequences of irregular sleep. Significant associations between mood, sleepiness, and nap duration also indicated that daytime naps may alleviate some of the negative effects of inadequate nocturnal sleep. So takeaway number 6 is that integrating consumer sleep technology with smartphone tools can significantly enrich sleep characterization. I'll next give an example of how we use CSTs in intervention. In collaboration with the Singapore Health Promotion Board, who are observing sleep patterns in a cohort of close to 2,000 working adults, we selected short sleepers with less than 7 hours time in bed and rewarded them for each night they achieved either one of two sleep goals: getting more than 30 minutes time in bed than their usual, or going to bed before midnight. We controlled this intervention group with a control group who just received general health education. Compared to the control group, participants were able to achieve the targeted sleep goals from weeks 3 to 5. However, significant societal obstacles to achieving these two simple goals proved quite formidable. And this work taught us that in order to transform sleep habits, we need to work at a societal level through companies, schools, and social networks to move entrenched values and habits, because otherwise people will just attribute their difficulties with obtaining sufficient sleep to work, leisure, or family commitments. So takeaway number 7 is don't just measure sleep, work to transform it using objective tools that we now have. So at the end of this presentation, I'd like to leave you with some parting thoughts. The first of which is to set fit-for-purpose standards for CST usage, differentiating health enthusiasts, at-risk persons, and clinical groups. The second point is to educate consumers about the above, particularly the benefits of trustable longitudinal data whose proper analysis will benefit all of us. The third is to anticipate novel use of sensors. This is going to be an exciting time in coming years where we will have more things to detect using wearable sleep trackers. This will be aided if we support and incorporate cross-modality data integration, and if we engage constructively with data scientists and engineers. I believe this will significantly enrich what everyone can get out of a consumer sleep tracker. And finally, I would encourage researchers and clinicians alike to examine cultural differences in sleep habits to better understand what good or optimal sleep means for different communities. It remains for me to acknowledge my very talented group, without whom none of this work would be possible, as well as our collaborators who have been a joy to work with. I would also acknowledge our funding sources, and if you want to find out more about my lab's work, please scan this QR code. I really enjoyed preparing this talk, and I hope you learned as much from it as I did preparing for it. And good luck with your studies and with your research.